Yeah, so as Stefano mentioned, there's more than deconvolution in fMRI. And I'm gonna be talking about neuroimaging data, but actually what I mean by neuroimaging data is roughly fMRI data, because there's data available in PET studies and everything, but mostly is fMRI data, okay? So, do you think we need to perform meta-analysis in neuroimaging? Because we know that in psychology, in social sciences, in biomedical sciences, we perform meta-analysis due to some problems that are kind of inherent to research. In neuroimaging, we actually need even more to perform meta-analysis because we have a problem, it's not exclusive of neuroimaging, but it's a big problem in neuroimaging. And that is, we were used to performing research that counts with many subjects and just a few variables, but for sure, having more subjects than variables allowed us to use classical statistics, the ones that we all learned in high school, university, and everything. But in neuroimaging, scanning a person is actually very time-consuming, very expensive, and also very annoying for the person. So we normally don't scan that many people. Up until 2010, most people didn't bother to scan even 20 people. You can read many studies with like 15, 12, 18 people. Nowadays, you get at least 20, between 20 and 30 is becoming the norm. But still, in the end, every voxel in the brain is going to be a variable that we are going to analyze. So we're going to have hundreds of thousands of variables and only 20, 30-ish subjects. And that's a problem because that changes the stats that we need to do and the things that we are allowed to do. But definitely having a small sample size, having just 20, 30 people in a normal fMRI study implies that we have very low statistical power. And since statistical power is a function of sample size and the effect size that we're measuring, and we're normally not that sure of the effect size that we're measuring, the thing that we can do, for sure, is to perform a meta-analysis that allows us to count with larger sample size. And of course, that will also help reproducibility in a way, and among other things. This is a non-exhaustive list of things that I think are important. It will help us reduce the high false positive rate that we have in fMRI research. Okay, so I guess you agree with me that we need meta-analysis in neuroimaging too. But is a neuroimaging meta-analysis just like any other meta-analysis in any other discipline? We would like it to be. We would like to have the raw data to perform meta-analysis using the images that people acquired in the scanner. But of course, that's normally not the case. Very few people share the raw data because it's also annoying. It's normally heavy. I mean, depending on the data set, you can get up to several terabytes even of information, and that's also inconvenient sometimes. But luckily, there are initiatives like the Open Neuro platform in which you can upload your raw data in bits format. And this can allow other people to reanalyze your data, to put it together with their own data and kind of like have a larger sample size. But yeah, this is something that we should aim for, but nowadays it's not an option actually. We don't have that many data sets available. So the second best thing that we could do could be to take the results of the studies, the statistical images that are normally the results of fMRI studies, and then just make a conjunction analysis that give us higher, larger, better statistical power. But again, this is also not the norm. There are some initiatives too, like the ANIMA database that was launched a couple of years ago, I think, that encourage people to share at least, even if you're not gonna share the raw data, because maybe you also want to keep exploiting yourself the data before you share it with other people, at least publish the statistical images so you can use them afterwards to perform meta-analysis. Still, if you check, I haven't checked actually, but there's no many data sets there. So we don't have the raw data, we don't have the statistical images. What do we have to perform a meta-analysis? This is an example from a study that I had to use for a meta-analysis of my own. It's a study from a group in Jülich in Germany, and they compared action observation to action imitation. And this is what normally people publish in the papers, right? But what we get actually to do our meta-analysis is just this, a stupid table with big coordinates. And this is all the information that we can use to perform a meta-analysis. So this thing called coordinate-based meta-analysis came to be kind of like a sub-discipline, let's say. And this is what I'm going to be talking about. Again, this is still feasible, but it's going to be limited because no many people share the data, and the same for this. So those are awesome ways to do meta-analysis, and actually better ways. But since we don't have the data, the most feasible option right now is doing a coordinate-based meta-analysis. Before performing a meta-analysis, you should always know that there's a lot of decisions that you're going to have to make along the process. And since we're always aiming for reproducibility and everything, I really recommend you that if you want to perform a meta-analysis, take a serious look at this recent paper in which basically every author that has been involved in developing methods for meta-analysis, they give a lot of advice. They provide like checklists, even an actual roadmap that you can follow step by step to perform your own meta-analysis. And okay, we know that it's going to be a bit complicated actually, that we're going to have to take several steps, especially if we want to be open about how we did everything. We know that we have coordinates reported in papers. What can we do with them? How can we compute the results themselves of a meta-analysis? Okay, let's imagine that we have a bunch of studies that we selected, that we are interested, and we want to perform a meta-analysis on them. Each of them reported a series of coordinates that are just specific points in space. They're just it, like dots. And some of them reported a few of them, some of them reported a bunch of them, whatever. We want to somehow combine all these points in space and make meaningful statistical inferences from that. But obviously you cannot just like get isolated points in space and make inferences about that in terms of cognition or brain physiology. What can we do about it? I'm going to explain these two kernel methods. This is the one that was developed, and this one was a bit later. There are more methods to perform a meta-analysis, but they are just basically variations of these two. So I think if you understand how this works, you will probably understand any paper on neuroimaging meta-analysis. Activation likelihood estimation was the first one that was developed, and is the most widely used, I would say. It does the following. Let's imagine that this is a 2D representation of an entire 3D volume with the coordinates as specific points in space, okay? So we have this study that reported a bunch of big activations, and we get the coordinates, this other study, whatever. What the activation likelihood estimation algorithm is going to do is, instead of treating these points as points in space, they are going to be the center of a 3D Gaussian distribution. Because we assume that even if a study was performed properly, you cannot be sure if the activation was exactly, the peak activation was exactly that point that they found or just the one next to it. We assume that there's a spatial coherence in the activation patterns. And we kind of like assume in this model that there's going to be a probability of voxels surrounding the one that was reported also being activated. Okay, then we're going to use probability addition rules to combine first per study how all those 3D Gaussian distributions overlap, and then we're going to transform that into a unique activation likelihood map. I don't know if it's clear enough. I try to make it the simplest thing, but I always like to see how things look in real data and in the brain because it helps me understand a lot. So this is from a meta-analysis that I performed. You can combine all the peak coordinates from the studies that you selected for your meta-analysis. Once you compute the activation likelihood estimate, what you get is this smooth map of those activation points, because then, as I said, we stop considering those as just points, isolated points, and we assume that it could be more like a distribution, okay? And then afterwards, we're gonna talk about that afterwards. We're gonna do some inferential statistics to see from those, because pretty much you get the entire brain covered by activation likelihood maps. We're gonna do some inferential statistics to see which are expected or shocking enough, unexpected or shocking enough to be meaningful to us. That was the activation likelihood estimation algorithm. The other one, multi-kernel density analysis, is very similar, but it tries to account for a thing that a lot of people were not happy with activation likelihood estimation. And it's that, as I said, maybe some study only reported a few data point, peak coordinates, and on some other reported a lot of them, even in the same brain structure. So how can you kind of like weight, give different weights to that? So these guys, instead of treating, I hate this. Instead of treating in the same situation as before, instead of treating the coordinates as 3D Gaussian distributions, they just make this is actually not a good depiction because they just make a sphere with a specific radius, and then they just account for every, they just take into account every sphere that has at least one peak coordinate within, but it could be 20. So they just care about like one or more peak coordinates within the sphere that they created to consider it as meaningful. So in that way, they end up actually diminishing the importance of those studies that reported a lot of activation points compared to those that just activated the maximum peak of just one blob, one cluster, okay? But roughly speaking, if you do both, the results are basically the same. They really don't differ that much. Okay, that's how you actually compute the meta-analysis with the data. But how do you perform your own meta-analysis? That is, if you go tomorrow home or tonight and you want to perform a meta-analysis, what do you need to do? I'm going to speak about two databases that you can use to run a meta-analysis. The first one is the Brainmap database. It was developed by people in the States, together with some people from Germany, and it is based on these three tools. The first one is to introduce stuff into the database. You normally don't care about it unless you're very, very generous and spend your time increasing the database. But normally we're just lazy and take what is already there. Oh, it's actually wrong. This is the one that you use to put stuff into the database. Then you use this one to search in the database, and then this one to compute the activation likelihood estimation of the data that you selected. The rationale behind the database is there are real human beings, this is not automatized, taking papers I don't really know how they select them. Maybe they think they're the most important or something. And then they used, as I said, this scribe little program to get all the information that they can. And trust me, they're really exhaustive. I will talk about the information that you can find in this database a bit later. They put all the information into the database. You're gonna find both functional data but also structural data to perform voxel-based morphometry. And then, as I said, you search for the ones that you're interested in for your meta-analysis. You perform your kernel method. They always use activation likelihood estimation, and that's actually why the name is there already. And well, they also developed a viewer, but that's totally not important. The thing is, they have a lot of papers, 3,500 papers, but you know, each paper can include different contrasts or even different experiments. So that actually includes more than 3,500 data sets, let's say. It includes up to, I can't read from here. Oh, I didn't say, it's, yeah, 17,500 almost. And this is what I like the most about this database. I think I have an image here. Oh, but it comes later. Okay, then I'll talk about that later. This is how it looks. It's just a GUI. It's just a program that you can use. You have some fields where you can input your search parameters. You can put everything. Like, do you want healthy population? Do you want pharmacological interventions? Lesion patients, whatever. Do you want studies that use only FSL for the data analysis? Like, you can constrain the search for anything that you want. Then once you do it, you just click on search, and then you get this table with all the studies that fulfill those requirements. And you probably can't read from there, but also you have this sidebar here in which you can see all the information, the meta information that was coded for each one of those studies, and also this kind of like human readable explanation of the experiment. So that's even cool to just have an idea of the literature, just kind of like a summary of the papers that might be interesting to you. Once you should check this, of course. Maybe one of the studies is not what you're looking for or something, so always check for it. And once you have the selection of the studies that you want to include, you download them, and you're gonna download a file that you just have to input into GingerRail, and it's gonna be as easy as, obviously you can customize some things, but as easy as to click on compute. You can obviously change from false discovery rate to family-wise error rate correction, or the threshold that you want, whatever, and a couple of more things, but it's just that. You downloaded the studies from the database that you wanted, and then you just compute the meta-analysis and obtain your images showing the statistically significant results. And as I said, there's something that I really liked about this database, and I'm a psychologist, and it's that it's coded for the, let's say, psychological process that we assume is involved in the experiment, and also the experimental paradigm that was used in this experiment. So even if you're interested in something in particular, you might not be interested in every test that we have for that function. You might be only interested in, for example, go, no-go tasks. That was the data, the brain map database. The other one that I wanted to introduce to you is Neurosynth. Maybe you have heard of it. Yeah.
Can I ask you something?
Yeah, sure.
Are the analyses run in Talarak space or
In MNI space, and I think it automatically transforms in the database from that. Oh yeah, sorry. The question was whether for the camera, whether the analysis is performed in Talarak or MNI space. The analysis is performed in MNI space. I can't hear you from here. And it includes a transformation from Talarak to MNI to automatically do that. So you don't have to take that into account. If you do manually, for example, if you just use search engines to select the studies that you want to use, you will have to do it manually. But this takes care for that. Yeah. Yeah. Then Neurosynth is a really cool tool, but it's just the opposite to the BrainMap database. It's automatized, so it's way more powerful. If I think they were like 3,500 papers included in the BrainMap database, this probably has like hundreds of thousands because it's automatized. They just do text mining and get, how they say, scientifically interesting words from the papers or something like that. We will see that later. So they automatically screen papers and they kind of like categorize, for example, let's say, okay, pain. We're gonna be using pain later during the tutorial. How many times did this paper mention the word pain? If it has a high frequency of the word, it considers a relevant paper for that. And then automatically gets the peak coordinates from the tables of the study and includes that in the database that you will use for the meta-analysis. This also has a GUI-ish. It's a web page. You can go to neurosynth.org and just run the meta-analysis from there. You search for whatever. I think I searched for autobiographical here. It tells you how many studies there are in the database for that term, and then you just get the result. They give you, for example, like different statistical tests to see which one fits you better instead of for your interests. You can also use some interesting tools. For example, if you're not too fond on neuroanatomy, it gives you a lot of information. For example, like what is this region that I just found activated? And you can play around with the thresholding and stuff like that, okay? But that's not fun. I mean, we're here for the brains, but also for the hacking. So get your laptops. We're gonna be doing a meta-analysis right now. Let's see if this works. And then we do it, okay? We're gonna be using Python. You already had some experience yesterday and the day before. We're gonna need some libraries to navigate through the operating system and managing files. Then we're gonna be importing the Neurosynth API to perform the meta-analysis in Neurosynth. And then we're just gonna plot the results. So we're gonna need some neuroimaging specific. You don't need to code this. We're gonna do it in a minute. We're gonna plot the results, and we're gonna need a couple of libraries for that. Okay. Then we need to get our data. So there's one thing that you're not gonna have to do, because if you all try to do it, we're gonna break the virtual machine apart. So the first time that you want to access the database, you're gonna have to download it with this line here, and then attach the features, the search terms to it. But then the most useful thing that you can do is, if you have 600 megas spare on your hard drive disk, is to save that database into your computer. Because this is gonna take, I mean, in a normal computer with good Wi-Fi, it's gonna take at least 5 minutes. Right now, it would probably just not happen. So I already saved the database into this file, so you're just gonna load it, and it's gonna take, hopefully, 5 seconds. Probably more. But yeah, we're gonna load the database. We're gonna get the feature names. The feature names are the search terms that you can use. And then we're gonna define our search interest. In this case, I suggest using pain studies. We're gonna see how many studies do they have on this, and then literally this line here is just performing the meta-analysis. That is running a meta-analysis. The other one is to save the results, and this one's for the plotting. Okay, so let's get to it. Can you see from there? Can I zoom in from here? No, right? No, actually no. Okay, I'm gonna read it out loud. So, as I said, we're gonna be needing to import. If you are already into the virtual machine, you're gonna have to do the conda activate MNE. So we have everything that we need. And then I haven't been here in all the talks, but I think you've been asked to do stuff in Spider, probably also in raw Python in the terminal. You know, there's always a million ways in which you can work with Python. I like to work with IPython because it's colorful and makes everything easier, and also the magic functions. So once we're in Python, are we all in Python? Yep. Okay. We're gonna need to move files around, so we import OS and we import shat.il. This is to make sure that we have the folders that we're gonna need, or otherwise we create them or delete them or whatever. Then, yes, OS and shat.il, SHUTIL. Wait, let's do this. It worked in my computer. Otherwise, we switch to stupid get it. Yeah, whatever. Okay. Wait, let's put this. Okay, so I'm gonna be writing on the left, so you can see. Oh my, seriously, what is your problem? I can only decrease but not increase the size of this. Oh, awesome. Okay, now, seriously, what's... Okay, wait. No. I'm a grown-up, you know? I can do my thing. I think the script is here, right? Nursing, and then it should be this. Yes. How was the name of that? Beam? Doesn't like the ampersand. Okay. Yeah, but then I need another terminal to execute this. How do I close it? Control X doesn't work. Q doesn't work either.
Column and Q, and then you enter. Q. Yeah, like that.
Okay. Can we get... Oh, I actually can use the slides, but not in... Want to give you again? No, discard. Okay. Almost there. Can you see better now? Even though these are not the commands that we're going to be using. These ones. Stupid operating system. Okay, so again, let's go to Python. We import OS, we import chat-il. We're gonna import NurseInf itself. But also, for the sake of simplicity of use, we're also gonna, what is your problem? Okay, whatever. Stupid virtual machine. We're also going to import specific functions from NurseInf, so we don't have to type the whole thing later. The function meta is the one that is going to do the meta-analysis for us. And this one is going to help us. Well, actually, we're not going to need it now because the data is already there, but for you to have it. Then we're gonna need Babel for managing Nifty files. And we're gonna use Nylearn to plot because I love the plots from Nylearn, even though they hate people like me just using Nylearn for plotting. Nylearn is an awesome library. You should use it for other stuff apart from plotting. This is not a Spanish keyboard? What the? Are you kidding me? Okay, whatever. Let's try. Okay, do we have everything imported? Okay, I'll give you a minute. But I guess it doesn't affect if I increase the brightness here to there, right? Most likely. Yes. Do you want the explanation or just for me to speak it up? Okay, sorry, wait. These ones. Shit, I deselected. Can you see them here? Okay, wait. Import OS, import chat-il, SHUTIL, import NurseInf, you can abbreviate it as an S. Import from NurseInf.analysis, import meta. From NurseInf.base.
Open the stream when it's there. Read it on the stream.
Is there any other way? Seriously, why? It didn't actually open Atom in the end, right? No? What happened to get it? It's like, that's get it somehow. Amazing. Are we there yet? OS. On the? Okay. Oh, but I don't want to erase what Thomas, it's super beautiful, I mean, okay.
Yeah, you can, it's okay.
Don't we have an eraser?
Yeah, but you really the thing that you did with going from...
Do I have to use my hand to
the graph?
Do I have to use my hand to... Oh! Good point.
Or if you want, you can go to the repo and download the Python script.
Yes.
And you can open it in your computer.
And probably I can zoom in. Better now? Can you see? Okay, so once we import everything that we need, this is my folder in the virtual machine, just put yours. Otherwise, it's not going to work, of course. And then, as I said, the first time that you have to download data from NeuroSynth, you're going to have to do it in one way, but it's slow in normal conditions, so it's going to be hell today. I already downloaded it for you, and yes. Actually, can I edit this? No. Yeah, that's the thing.
You can edit that. Go up for hacker. There, edit.
Cool. Yeah, this. Okay, yeah.
Yeah, log in. Show us your password.
Do I know my password? Oh yeah, I don't know my password. What? Oh without the Spanish symbol. Awesome.
Without the dot and without the at.
I don't know if I can actually type my password with I mean, it has symbols and I don't know where they are here. I'm gonna try. Yeah, I know the password, but it's not a Spanish keyword. So let's try. Ooh, amazing. Okay, so we're in. Did everybody import all the libraries that we're gonna need? Okay, cool. Yeah, remember, you change this to your name, to your whatever, you know. And then we would have to run these few lines to download the data for once. But if you actually go to the terminal and go see what we have in materials in Python, yeah. If you go to materials, fMRI, neuroimaging meta-analysis, and then NeuroSynth, you should see a bunch of stuff, the script itself, and then the data that I originally downloaded from the NeuroSynth database, and then the compressed dataset that we're gonna load, okay? It's called dataset.pkl. So to make things easier, one thing we can do is take that path and put it into an environment variable. Let's call it data. Can I put this? Yeah, better. Can you see what I type here? Okay, so we can put it into a variable like a data directory. It's gonna be damn. Why do you do this to me? Okay. Yeah, if you already have this variable here, I'm gonna update this plus, as I said, materials, fMRI, neuroimaging, okay? And it didn't work. Oh, wait. A stupid symbol, seriously. Why do we have a... it's plus, okay, whatever. I didn't. I don't know where commas are. Is this? Yes, awesome. And this. Wait, where's the slash? Here. Okay. Oh, I didn't define it. Good point. Did you do it? Our home directory, the one from our home. 251. This is mine. You put yours. And then we get the data directory. Now we are ready to load the data. we're gonna create our data set with that data set function that we loaded before. And then data there, plus. Are you following, guys? I think it was dataset.pkl, right? Can I use my computer? Yeah, okay. Let's do this. Follow me as I type. As I said, we need our data, and our data is in a folder in the virtual machine that is in this path. It should be for you. Once you have defined the home directory, everything should be the same for you as for me. Materials, fMRI, neuroimaging, meta-analysis. Then we here load the data set. Well, actually, someone didn't update my script. You should need this line to load the dataset. Once you do it, let's actually do it the stupid way. I cannot also paste anything. That's brilliant.
Press the right button.
Okay. There is no such file. Oh, because I always make this mistake. Here. Okay. Okay. Now we have our data set. As I said, NeuroSynth has these features, they call it. It's the search terms that you can use. You can explore them with these lines. Didn't I? I know, you're totally right, yeah. What is wrong with this? Thank you. Amazing.
You don't put the NeuroSynth folder. You are in the meta-analysis / NeuroSynth.
Oh, yeah. Good point.
Yeah.
Okay, so now we should get our list. We shouldn't, because there's probably something stupid wrong. Where? Yes, exactly. I'm gonna kill someone for this keyword. Yeah, I know. Neuro imaging. Let's go the quick way now, hopefully. Okay, we're getting our data. And as you can see, we get a list of a lot of topics, let's say, that we can use for our meta-analysis. You can literally use everything. You can even use logic if you want to use the conjunction between different terms, or this but not that, or whatever. We're gonna be using this one on this old version of my script that I made 2 weeks ago, and not the one that I made for this, but it's gonna be on decision-making studies, okay? So if you run these lines, it gets into this object here, the all the studies that have at least the high. Actually, this is probably the highest frequency. You have this attribute in the get studies function to see, okay, how frequent do you want the search term to be in the paper? Are you kind of like liberal and it's okay if it's just a bunch of times, or you want only papers that talk a lot about this search term? So you could put, for example, 0.1 instead of 0.001. You would get more studies, but then it's probably, you cannot be sure that you're just getting what you aim for. Yeah, and as the second line says, we found 949 papers with a decent amount of mentions to the SISH. It includes decision making, decision, this, I don't know, whatever. And we are gonna run these lines just to make sure that we have the folders that we need to export our data. And as I said, this line, just one line, is the one that is performing the meta-analysis. You provide the data set that you created with all the studies that have this search term that you included. Wait, no, the entire data set and the selection of features that you selected, okay? You can save the results. And just to see how it looks, we can plot it with Nylearn. And you get a meta-analysis of decision-making studies. That is, this is how it should look like if you're interested in decision-making studies. You should probably find these regions activated, for example, consistently. In a single study, of course, it's not likely that it's going to be exactly like this, because there's always a lot of stuff that can influence your study. But let's say that that's a quick and dirty way to run a meta-analysis. This is actually, we haven't made any proper inferential statistics in this. Neurosynth does this, but this is just the posterior of the probability of getting each, the posterior of the probability of getting pain, or pain was in my example, decision making as a label in a study that activated each one of those boxes, okay? But that's not, it's not corrected for like false discovery rate, it's not corrected for family-wise error rate, but it's something that you can just use to have a look at for example, how the typical activation pattern of a specific field that you want should look like, okay? And then I'm only gonna mention this because we don't have the time, and also because it's actually not too good. The people that develop all these tools, they're now developing this other library, Nightmare. I guess it's Red Nightmare because the logo of the library is a spider. And it looks really, really well. It's gonna integrate both the data from the Brainmap database, data from the Neurosynth database. It's gonna allow you to choose whether you can you want to use activation likelihood estimation, multi-kernel density analysis, or any other kernel method. And it's gonna also allow you to do more with this, because doing this analysis, this meta-analysis, is good to see, for example, how the, let's say, the canonical brain response to a specific concept should be. But then, for example, you could use the coordinates from the results to build your own seed regions for connectivity analysis, or to make ROIs if you are interested in doing ROI analysis. And that they're building also functions in this Nightmare library. So I really suggest you, if you're interested in meta-analysis, that you have a look at this. I'm just gonna see if I can copy-paste this and see if it works. Probably no, right? Yeah. So I'm not doing it. I'm just closing this and
And in the meantime,
yes.
we can already thank you very much, Daniel, for your tutorial.
No. Anyway, I hope somebody uploads the proper scripts to the repository. You will have them.
You attended the gift class, right?
What?
You attended the gift class, right?
Yeah, I can actually do it myself. You're right. But yeah, have a look at the scripts. They work, I promise. And yeah, just pay attention to this library because it's probably going to be one of the things that is worth revisiting in a few months.